In this video, we are going to implement a hardware accelerator for the FFT function that was earlier designed using Vivado HLS. What that means is that we will start by profiling the FFT software function using the performance counter module that we implemented in Vivado. Customize the FFT Vivado HLS IP, first to convert it to floating point, and secondly to add an AXI-Lite interface instead of the AXI-Stream interface so that it can communicate with the Microblaze processor. And finally, we will attach it to the Microblaze, implement it on the FPGA and compare the software and hardware outputs as well as speed. There are a few requirements to complete before you go through this particular demo. One is you should have completed the performance counter demo, which basically implements a performance counter using Vivado HLS and then integrates it with Vivado. The second change that we are making is that the number representation we are going to use float instead of AP fixed. This is due to limitations in the Vivado SDK and also the Microblaze processor itself. The processor does not have native support for the AP fixed data type. So to keep this demo simple, I am going to use float instead of trying to emulate the AP fixed functionality. The Vivado project that we will use will be a continuation of the same performance counter project that we had earlier. In fact, for the initial software profiling, we will not make any changes at all to this Vivado project. We will just change the software alone. You might have to look through the GitLab source code in order to find out exactly where the SDK source is stored. Part of the reason for this is that I'm also reorganizing the source code a little bit from one demo to another. So it's possible that the files have moved around since the time that the demo was recorded. However, it should be fairly obvious to you once you see the files that they are meant for use in the FFT demonstration, and these are SDK source files. The files that we need, if you look at them, you will realize that they are all very similar to the files used in the Vivado HLS project. The same file names: 32fft.h, 32fftvalues.h, fft.cpp, inpcpp.txt and out_cpp.txt. These two were created using our datagen script. And finally, instead of the fft_tb.cpp, I now have a file called main.cc, which, if you actually look at it, you will realize that the contents of this are exactly the same as that of the fft_tb.cpp, slightly modified so that it can run on the Vivado SDK. The simplest way to get these files into our SDK source folder is that you open the folder where you had created the hello project that we used in order to run the counter. You will find that there is a folder over there called hello.sdk. Inside that, there is another folder called perfctr. This was the name of the software project that we used for the performance counter testing. And if I go in here, I can copy all the files over from where they were in the GitLab source code. Once you have copied all the files over, you will find that the main.cc shows up in in the SDK folder. You might find that it gives a message such as file changed, in which case you can just say, do you want to replace the editor contents with these changes? Go ahead and say yes. Now, when you look through the SRC folder on the left hand side, you will find that all the files are there. 32fft.h contains pretty much the same as what we used for Vivado HLS. The only difference here is that the data T is now type def as float instead of AP fixed. 32fftvalues.h is completely unchanged. fft.cpp is mostly unchanged except for the fact that the directives that were used in order to set the interface conditions have now been removed. The main.cc file is a modified version of the test bench that we used for the FFT in the Vivado HLS. The modifications are fairly obvious when you look at them. One of them is the fact that you can see the X counter. This is used for the actual performance counter, similar to what we used in the demo for the performance counter itself. The more important changes are the fact that the inp_cpp.txt and out_cpp.txt cannot be read from files. Therefore, the files that we are using over here are modified versions of the ones generated from the datagen script. they have some additional information over here that tells us that these are actually complex numbers of the type data underscore comp. Both INP CPP and out underscore CPP have been modified suitably for this. In the present case, I have already given you the files required for the demo, but feel free to modify the data gen Python script so that it directly generates the data in the format that you want. Now, if we go through this test bench, what we see is we basically initialize the counter out here, and then the main work is being done in this particular line, which is just calling FFT, passing in the data in and getting the data out. I call two timers, that is T1 is called just before calling the FFT function and T2 is captured just after the FFT function. I then go through this process where I check the final results. In this case, just for clarity, I am also printing out the entire result that the real parts of the values that are being generated, just so that you can confirm visually that the data actually turns out to be the same. You will notice that I had to create one extra function over here called dispf in order to display floating point numbers. The reason for this is that the xil printf function does not have the capability of printing floating point numbers. The rest of the test bench the rest of the main function looks similar to the Vivado HLS test bench, except for this last line over here where I print out the number of software FFT cycles, that is the number of cycles taken by the software function for the FFT routine. Now, in order to run this, we go through exactly the same process as before. I need to make sure that my minicom is running as usual with all the settings set up correctly. And once I go back over here, I can again select GDB debugger on local, and it straight away goes and runs the code. And once that has completed, I can go back here and look at the outputs that were generated. It essentially prints out these values, and you can see that the output that was generated in the software as well as the expected output match perfectly. The most important part over here as far as we are concerned is this last line, which says that it took 559,000 clock cycles in order to complete the entire FFT routine. Now, this number is actually very large. And why is it so large? The main reason, if you think about it closely, is the fact that the Microblaze processor does not have a floating point accelerator. It does not have the native capability to perform floating point operations. Therefore, even a 32-point FFT, which should have taken maybe a few thousand clock cycles, instead ends up taking 500,000 or more than 500,000 clock cycles. The next step that we are interested in is to create our hardware accelerator and compare that against the software. For that, I am once again created a Vivado HLS project with the FFT code. The only real difference that you will see over here if you open the 32fft.h file is that now the type def is set to float. This is so that it is compatible with whatever was done in software. The fft.cpp file itself is exactly the same. The only changes that you have to make over here are remove the directives that were originally there and instead insert directives for the interface and set the mode to s_axilite, that is a slave axilite interface. In this case, I have already done that. I am also specifying that the destination for the directive is the source file. Having done that for the port equal to return and also for the data in as well as the data out ports, I find that there are 3 lines that are added over here as hash pragmas. This will result in the final FFT code that is being synthesized having an axilite interface, which will allow us to start it as well as to send in data as well as to get the data out finally. We can go ahead and synthesize this and package and export the IP as usual. One thing to note after synthesis is that the latency over here is expected to be 1700 clock cycles. Once again, I have not applied any kind of optimization directive, so this is not really surprising. The number of block RAMs, the number of DSP slices, the number of flip-flops, etc. I'm not going to go into analyzing these because there is no particular optimization that has been applied, and given the fact that it is now using floating point rather than fixed point, we can generally speaking expect the resource usage to be higher. The interface itself is now completely axilite and only the clock and reset are non-axis signals over here. I'm not going to go through the process of RTL co-simulation, etc. It's strongly advised that you do so in general, but for this demo I'm going to skip that. Now we export the RTL. We could of course change some of the configuration values that we wanted over here, but I'm just going to leave them at the defaults. And once the RTL has completed export, we can close Vivado HLS and now go back to Vivado to import the IP. Now we are back in Vivado. Once again, similar to what we did in the case of the performance counter, we first need to go and change the IP repository and add the repository where we had created the FFT. Choose the folder where you ran the Vivado HLS project. It identifies one IP over there. We can click OK. Now that this is done, I can go back to my block design and add an IP and search for FFT. When I select this, it shows up that this was the repository where I had created it using Vivado HLS. Double click on it. It adds the IP and gives me the option for run connection automation. Go ahead and do that. Regenerate the layout to clean things up, and now you find that on the right hand side, essentially now things have cleaned up. We basically have the 3 axis interfaces that are there. So there is one for the FFT, one for the performance counter, and one for the UART itself. The next step of course would be to complete validation of the design. Save the design and go ahead and generate the bit stream, because we have not made any other changes at any of the levels. Once the bitstream generation has been completed, we go through the same process again. We need to export the hardware and we can then launch the SDK. Within the SDK, once again, to keep things simple, it is best to close the previous projects and start a fresh application project. Make it a C++ project, because once again we want to be able to run the code. And the reason why we are creating a fresh project is so that the board support package will now be updated with the information required for the FFT module as well. Start with an empty application. And when you look at the BSP, you can see that it contains the FFT, UART Lite as well as the counter modules. When we go in there and look at the BSP source code in live SRC, we find that there is an FFT module. And once again, when we open the xFFT.h file, we find that similar to the counter, there are a few functions: initialize, start, done, etc. And also functions that allow us to write the real data, write imaginary data, and similarly to read back the data out, the real values as well as the imaginary values. We will be using all of these functions in the final application that we are going to use for testing the software as well as the hardware. The source code for this is also available. You can follow a similar procedure as we did for the software testing with the performance counter to copy the files over into the source directory of the FFT perf project. In other words, replace the files that are currently here with the files provided in GitLab. Once you have copied over all the files into the SDK/FFT-perf/SRC folder, you can right click on the SRC tab over here and refresh to make sure that the list of files get updated. Now if you open the main.cc, you will find that in addition to the previously existing main function, a few more functions have been added, mainly write to FFT and read from FFT. Inside you will find that the write to FFT basically takes in the floating point values which have to be passed as two floating point arrays, and writes them respectively into the real and imaginary parts of the FFT hardware. Similarly, the read from FFT uses another two API functions to read back values from the FFT module and store them into two other floating point arrays. What are these floating point arrays? If we go to the main function, we find that I have now defined two new arrays, in_r and in_i, and similarly out r and out I. And all that we need to do is, once we have loaded in the data _in, we need to copy those values over into in_r and in_i. The reason we do it this way is because the complex data type does not store the real values as one continuous array of floats, which is what we require in order to make effective use of the writewords API function call. This part is the same, except that I now also have the FFT initialization, but after that we just go through the counter initialization as before, and this portion executes the software and computes the total time taken for running the software. I then check whether the software gave the correct results, and in this case I have modified the code so that it will only print out a value if something does not match with what was expected. You could modify this if you actually wanted to see what was being actually computed by the function. Now comes the part where we want to invoke the hardware. We run a few counter values T1, T2, T3 and T4. Those are self-explanatory in terms of where they are placed. The important functions are write to FFT, which takes in the XF pointer that we created out here when we set up the FFT module, and what it does is it takes the in_r and in_i arrays and writes them into the FFT module. After we write, the next thing to do is to actually activate the module. This is done by calling the xFFT start function. The next thing that we need to do is to check whether the module has completed operation, and the way that we do this is by continuously polling the xFFT is done function. I have just added a counter over here so that in case for some reason the xFFT is done does not pass, it would print out an error after a certain timeout has completed. On the other hand, if it does pass, then nothing gets printed out. The reason why I am commenting this xil printf is because I want T2 and T3 to actually capture the time required from the start of the FFT until the done signal has come back, and I do not want the time required for the printf to also be accumulated inside that. And finally, we also have the read from FFT, which pulls back the data from the FFT module back into the SDK code. Once again, just like we did for the software, we will compare the values. If either the software or the hardware did not pass, we would print an appropriate fail result. And finally, we will print out the values corresponding to the number of cycles taken by the software, the number of cycles taken to write data into the FFT module, the number of cycles taken to actually compute the FFT, and the number of cycles taken to read back the data from the FFT. In order to run this, we can once again go to the run configurations. Remember that the application now has to be updated so that the project is now the FFT perf application. Once we have done all of that, we can go ahead and click on run. Go back to the terminal, where we see that first of all, the first message that is printed is pass. In other words, both the hardware and the software successfully computed the FFT without failing the tolerance limits. The number of cycles taken for the software was 559,805, which, if you recall, is exactly the same number we saw earlier when we profiled the software code. In contrast, the total time required for the FFT computation is 1200 cycles for writing the data, 1900 cycles for computation, and 1200 cycles to read back the results. This 1900 cycles that you see over here is close but not exactly matching with the value of around 1700 that we estimated in terms of the Vivado HLS. Part of the reason for this is because there are some function call overheads when you invoke the function from the C code. The actual time required for computing the FFT is probably 1760 clock cycles, but the additional 100 odd clock cycles are taken up for calling the functions that activate the FFT as well as for the polling that is done afterwards. To summarize, what we can see is that the time required for a software implementation of the FFT function is more than 500,000 clock cycles, whereas the entire time taken for the hardware implementation, including the time required to write the data into the FFT, compute and then read the data back, is a total of less than 6,000 clock cycles. Even in this, you will notice that the actual time required for the computation is roughly 1/3 of the total time, which means that the time required to write data into and out, get it out of the system itself is a significant chunk that cannot be ignored. This concludes the demonstration of implementing a hardware accelerator for the FFT. As you can see, the similar kind of techniques could be used in order to implement any other kind of accelerator as well. Part of the reason this particular accelerator was so successful, giving us nearly a 100x speed up, is the fact that the Microblaze processor does not have floating point accelerators and therefore takes a long time to emulate floating point in software. On the other hand, that also gives us a compelling reason why using the hardware accelerator was actually a good idea in the case of the Microblaze processor.